Constructing a free body diagram is the first step in modeling any static system, really solving any statics problem. In the real world, static systems always attach to the rest of the universe at one or more interfaces, and a free body diagram isolates the system that we're interested in, replacing its attachment points with forces and torques that accomplish the same job. In other words, if we cut this system out of the rest of the world, what are the forces and torques that we would need to add to keep it in place? A free body diagram consists of four things. We have a list of relevant forces, where we're deciding what goes into our system and what we're assuming isn't a relevant thing. So this is where we're deciding what we're neglecting and what we aren't. Next, we want to come up with a variable naming convention. And the idea here is we want to name each of the relevant forces using some variable. And we want to be systematic about that so that we can easily put these things into equations and use them later. Next up, we want to create a coordinate system so that we can all agree on which way is up and which way is down. And so as we start solving things, we can break them into components. And lastly, we're going to add arrows to the diagram to show the assumed direction of each force or each load. So for example, maybe we have this crane and it is experiencing two things. Over on this end here, we have some load that it lifts, and on this end here, we're looking at some sort of a counterbalance. So if we were to draw a free body diagram of this, following the steps here, the first thing we want to do is list the forces. The first would be that load, which is a weight. And so we have the load, and maybe the variable that we could give it would be W sub L for weight of the load. Another thing that it's experiencing here is this counterbalance. So we have the counterbalance, and we could give that the symbol W sub CB for counterbalance. So those are the forces acting on it. Next, we want to agree on coordinate system. And so one option, not the only one, is that we could go with X going this way, Y going that way, and we'll let everybody know that gravity points down in the Y direction. And now lastly, what we want to do is create a sketch of the system, and we want to add arrows that represent each of the interactions it's experiencing. So on the applied load side of the house, we have that load here, which we call W sub L. We have the counterbalance acting on this side, WCB. But that's not all, right? There's a mount that keeps this thing from falling through the earth or tipping over, and we need to account for that as well. And so if we call this base here where it attaches location A, we know there's probably some sort of a reaction force in the Y direction at A, some sort of a reaction force in the X direction, and because of the way this thing's mounted, it could also have a reaction moment at A, all of which's jobs are to keep this thing in place. This would be a complete free body diagram for this system. So here's the thing. Everything hinges on this diagram. The free body diagram captures all of the relevant phenomena that are acting on the system, and so if something is shown on the diagram, it needs to appear in your equations. And if it doesn't appear on the diagram, then it better not show up in your equations either, because you've chosen to neglect it. It also defines the direction of every interaction. So when we construct models of systems, we're always going to want to break things into coordinate directions, right? We'll look at the horizontal forces, maybe we'll call those X, and the vertical forces, maybe we'll call those Y or Z if it's a 3D problem. And then we're going to treat things that happen in each of those directions separately. So when we assemble our balance equations later on, it's going to be really important to use positive and negatives to correspond to which direction we drew the arrows. For example, in our crane here, we drew both weights acting in the negative y direction. So when we put those into an equation, we're going to write the equation with minus signs for each of those, a minus w for each of those. Now, in general, we're going to experience two types of systems in a static sense. We're going to look at particles, and we're going to look at rigid bodies. Particles are systems that can be treated as a point mass. We tend to draw them looking something like this, and the thing that's interesting is that their size or their extent is completely irrelevant. This is going to come in handy when we want to look at the overall behavior of even really complex systems, and the free body diagram for a particle is always going to look like some sort of collection of forces acting on a little dot like this, and of course we'll have coordinate system x and y. A rigid body, on the other hand, is a system whose size or extent does need to be accounted for. So for example, some long beam like this, and the reason that we need to account for that is that a force here creates a torque about this point over here. And so now we have the ability to do something called a moment, and that's only going to show up in rigid bodies. So the first thing that you can always count on, the most important thing, anytime you're trying to solve a static system, is to draw yourself a free body diagram that accurately captures everything you care about. This is the tool that gives you clarity.